big part of GCSE physics is knowing how electricity is made, and it's made with the process of electromagnetic induction. Okay. Now the definition of this is that it's the process of inducing an electrical current or voltage. Okay. Inducing means kind of creating, I suppose, in a way. And from the title, electromagnetic, you can probably see that it involves electricity, you're making electricity, but that it involves magnetism as well. So the electricity and magnetism are really, really closely related. They're both kind of two sides of the same coin, and they can be used to create each other. But for this session, we're going to look at how we can create electricity, and it uses magnetism. It needs three things. The first one is a magnet, because if you need magnetism, you're going to need a magnet to help you do that. It also needs a coil of wire. Now, coils are really great shapes for electric fields. Why? You don't need to know, but a coil is often really useful when you're looking at electromagnetism. And finally, you need some movement. So all you need to do is move a magnet near a coil of wire or in a coil of wire, and it makes electricity. So for example, here I've got 4 diagrams that look at 4 different setups. Now this is a coil of wire, and this is an ammeter. Okay, now an ammeter, remember, just measures current. And the ammeters that I'm going to be drawing today are going to be analog ammeters. So this is 0, and going one way is to positive numbers, so say +2, and going this way is to negative numbers, say to -2. So here I've got a magnet. Now a magnet, remember, has 2 poles. It has a north and a south pole. If I move that magnet into the coil of wire, I'll see that the ammeter does this. The ammeter moves from its 0 position where it was to start with, and it will go towards there, and it will produce a current. Now, as soon as that magnet stops, as it's still, so it's moving there, as soon as that magnet is still, north-south, that current goes back to where it was. It goes back to 0. So its magnet is still. Now, if I pull the magnet out this way, pull it out of the coil of wire, what I see is that the dial then moves towards this way. And if it's then still once again outside the coil, the ammeter goes back to where it was. So what I see is happening is, as you move the magnet in, the ammeter does this. It stops when it's still. As you move the magnet out, it goes to this side, then it stops as it's still. And if you move that magnet in and out of the coil of wire, basically like so, you see that the ammeter does this. It moves forwards and backwards. Okay, and this is producing current. Okay, now what's happening is that at this point, the current is going in one direction. So here the current is going, say, forwards. So that means the electrons that make up the current, because remember, a current is just a flow of electrons. I'm going to write them like that. The electrons are travelling in a certain direction. Let's say they're travelling in this direction. Then they're still. There is no current when the magnet's still. And when the magnets move back, the current flows in the opposite direction. It goes that way. The electrons travel that way. So the electrons in the wire, I'm going to quickly draw a wire. Lots of negative electrons in. There we go. The electrons are literally moving that way, and then they're stopping, and then they're moving that way. They're moving backwards and forwards. They don't actually travel in a complete loop. This is different to what you get with a battery, okay? So don't get too confused. When you've looked at electricity in terms of models, etc., especially at Key Stage 3, you'll think about direct current, which is a bit different. This current is going forwards and backwards. It's alternating. And for this reason, it's called an alternating current. So this process, EM induction, produces an alternating current, okay? We're going to look at that in a bit more detail in a second. But first things first, we're going to look at how we can make this current or voltage bigger. How can I make this ammeter go further over, to here or to here, instead of just to there? Now there's 4 ways I can do that. I can use a stronger magnet. If I use a stronger magnet, the magnetic field's bigger, it makes the current bigger. I can move the magnet faster. I can move it in and out of the coil of wire faster than it was before. I can use more coils of wire. So instead of having this, I could have this. That increases the current. Or I can add an iron core to the coil of wire. So I have the coil of wire here. I add in a core of iron underneath, and then I move the magnet like that. And this amplifies the effect. Okay, so there's 4 main ways I can use the stronger magnet: move the magnet faster, add more coils of wire, or add an iron core. I should probably get rid of that. Okay. Now this produces an alternating current. Okay. An alternating current, as we said before, is a current that goes forwards and backwards. And if I plotted that on a graph, I'd see something like this. Now, if you are good at trigonometry, you might see that this is a sine curve. Okay, so this means that here I've got my positive voltage or my positive current. I could also write either. And this is when I'm moving my magnet into the coil of wire. Here it's stopped. This is when I move the magnet out. Here it's stopped. Move the magnet in, stopped, out, in. If I move it faster, I'll see that these waves get closer together. If I use a stronger magnet, I'll see that these waves get bigger. And this pattern, this sine curve of plus and minus, remember this is positive and this is negative, is what's called the alternating current. That's what it's called because it's going forwards and backwards. Now, if I switch my magnet around, so instead of having the north pole going in and then the south pole going up, let's have a look here. So if I switch this around instead and had it north and south, the difference would be is that my alternating current would just go the opposite way. So my electrons would start going backwards and then they'd go forwards. So this is also known as AC. And it is what the band AC/DC are named after. So AC is alternating current, DC is direct current, and you get that from a battery. And that just means the electrons are all going the same way the whole time. Now, this isn't how electricity is usually generated using a magnet going in and out of a coil of wire, because that's a little bit hard, it's a difficult motion to get machines to do. So what they use is a generator. And a generator is it uses exactly the same principle, motion, a magnet, and a coil of wire. It has a coil here, and the coil is inside a magnetic field. So we can see here there's a north pole and a south pole, and there's a magnetic field. Now, this coil is usually attached, or is attached, to a turbine that spins. So this generator spins around inside the coil of wire, inside the magnet. So a generator is a spinning coil in a magnet. We've got motion, because it's spinning. We've got a coil of wire, and we've got a magnetic field. In a magnetic, I should write magnetic field there. So this also, sorry for my really bad writing, produces electricity. Okay. So a generator is just a more efficient way of doing this, an easier way of doing this for a bigger scale. So it has the same principle, it still uses a magnet, a coil of wire in motion, but instead of going in and out, it spins around because that's an easier motion to produce. So that's all that electromagnetic induction is really. You just need to know that it involves three things: a magnet, a coil of wire in movement to produce electricity, that it produces an alternating current that goes forwards and backwards, that can be made stronger by, or you can increase the voltage or current by using a stronger magnet, a faster motion, more coils of wire, or adding an iron core. And a generator uses this principle but spins the coil inside a magnetic field instead.